Hello everyone, welcome back. In this lesson we are going to learn about a numerical method that is very much frequently used to solve with simultaneous linear algebraic equations, and this is the Gaussian elimination method. So first of all we are going to learn about the basic Gaussian elimination method, which is also known as the naive Gaussian elimination method. So let's dive into the details of this method. There are two steps of naive Gaussian elimination approach. The first step is to eliminate the unknowns, and the second step is to solution the unknown variables through back substitution. So I guess you do not know these two steps, but we will know the details of these two steps in more details in the next few slides. So first of all, in step 1, which is also known as the forward elimination approach. In this case, if you remember the general notation of a system, a linear system which contains n equations, there are going to be constant coefficients of unknown variables, which are a11, a12, a13. These are the coefficients of unknown variables. We already know this from the previous lesson. So with those constant coefficients, we are going to form a coefficient matrix, which is also known as the D, which is denoted as D in the previous lesson. If you remember, we denoted this with the Cramer's rule. So once we get the coefficient matrix, in the first step of naive Gaussian elimination method, we are going to transform that coefficient matrix into such a matrix, which is an upper triangular matrix. So from our original coefficient matrix, we are going to find out a new matrix, a modified matrix, which is an upper triangular matrix, a modified version of the coefficient matrix. So this is the first step. This is the first step to modify the coefficient matrix. So the question is how we are going to find out this upper triangular matrix. So let's see into the details of this approach. First of all, we have this system of equation. There are n equations, and the coefficients of unknown variables are a11, a12, a13, a21, a22, and so on. These a terms are the coefficients of unknown variables. And what are the unknown variables? x1, x2, x3 up to xn. And also on the right hand side of these equations we have the b constants. So if you remember, to get a upper triangular matrix, all the elements below the principal diagonal will vanish. So that's the definition of upper triangular matrix, that all the elements below the principal diagonal of the matrix will be 0. So these two, all the elements that is under the value of under the principal diagonal, they are going to be 0. So that's the main purpose. So how we are going to make them 0? For example, in the first equation we have the coefficient a11, and in the second equation we have the first coefficient, which is a21. So in our modified upper triangular matrix, this term will be 0 because it is below the principal diagonal. So how to make this element 0? We multiply equation 1 by a21 by a11. So if we multiply the whole equation 1 by this value, which is a21 by a11, and then if we get the result, we will see that a11 in the denominator and in this a11 will be cancelled out, and we will have only the term a21. So once we multiply this first equation by this term a21 by a11, we will have only the term a21 remaining, and then we will subtract these two equations. We will subtract the first equation from the second equation, and this term will be vanished. Okay, so in this way we can easily eliminate this term, which is under the principal diagonal, to be 0. Okay, so this term will become 0. So this is the equation that we will get once we subtract. For example, in the second equation we are going to subtract the first equation from the second equation after multiplication, and in the first term we will have this a22 minus a21 divided by a11 into a12. So in this way we can get our second equation, second modified equation, which will have only the terms which are from the second to last. That means the term which is below the principal diagonal will be equal to 0. So after the first step, after the first elimination of the first term from the second, we will have this second equation, a22 prime x2, a23 prime x3. So these are the some new form, new notation, new coefficients, a22 prime, a23 prime, because the original coefficients are changed now, because we have multiplied the first equation by some parameter and then we subtracted that first equation from the second equation and we have got a modified second coefficients. So these prime notations are used to denote that the values have been changed. Similarly, we multiply the third equation by a value which is with the same parameter. That means we multiply the first equation by a11 divided by we multiply the first equation by a31 divided by a11. That means a11 will be cancelled out, only we will have the a31 terms, and then we subtract the first equation from the third equation and we will get a new version of the third equation. So in this case we multiply all the first term, we multiply by these first terms with the first equation and we will get a modified version of this original coefficient matrix. So look at this, all the first terms have become vanished. That means we have just vanished the first terms below the principal diagonal. Similarly, we will have to vanish these terms, that means a32 prime to a and 2 prime. These terms will have to be vanished as well to get a closer to the upper triangular matrix. So remember, for these foregoing steps that we have covered, the first equation is termed as the pivot equation because we are not changing the first equation. Okay, so for the first step we are just vanishing this first column. So for this case the first equation is the pivot equation, and this a11 coefficient, this is the pivot coefficient. Okay, so if you remember, in all of these multiplications we are just multiplying the first equation, which is some coefficient divided by a11. So in all the multiplications in the denominator we have the term a11, and that's why it is called the pivot coefficient. Okay, so dividing by this pivot element is also known as the normalization. So after the first step we are going to vanish the second column. So how we are going to vanish the second column? In the similar way that we did for the first column. So once we do, we will have this again a modified version, but in this case we have the first two columns are 0 under the principal diagonal. So this is the second step. Then in this way we are going to approach the nth equation, and we will see that in the nth equation we will have only one term remaining and all the terms before that will become vanish. So now if we look at this modified version of the original coefficient matrix, we will see that this is a upper triangular matrix because all the elements below the principal diagonal have become 0 or vanished. So next we are going to go into the second step of our naive Gaussian elimination method, which is the solution by back substitution method. So how we are going to use this? So once we converted our original coefficient matrix to an upper triangular matrix, so if you remember, the last equation, that means the nth equation, has only one term remaining, and the nth equation is something like this. ann n minus 1 xn equal to bn to the power n minus 1. So in the superscript we are seeing that we are using the notation n minus 1. What does this mean? That means we are getting this result after n minus 1 steps in the elimination method of the first step of naive Gaussian elimination. That means we are just using n minus 1 steps to get these coefficient. Okay, so this is a very straightforward equation. We can easily get the value of xn, which is we divide the value of bn divided by a coefficient. So we get the value of xn from the upper triangular matrix in a very straightforward manner. So once we get the value of xn, we will just substitute these xn value in the n minus 1th equation in the upper triangular matrix. In the upper triangular matrix, the n minus 1th equation has two unknowns. Those unknowns are xn and xn minus 1. So we already know the value of xn. So if we substitute the value of xn, and then we will get the value of xn minus 1. So in this way, we just carry out the calculations from the last to first equations in the upper triangular matrix, and we easily get all the unknown variables. That means unknown x variables. So I guess you are very much overburdened by the calculations and the formulas that we are seeing here. So this is the general formula of the back substitution method. This is very straightforward. So if you just think about this equation, you will understand that this is just we are just finding out the last x terms, and then we substitute the x term in the previous equation, then we just substitute in the next previous equation. So in this way we are just calculating from the last equation, and that's why it is called the back substitution method. We are just finding out the last unknown variable first, and then we go backward, and that's why it is called the back substitution. So I guess this description that I have given is very much overburdened. So once we get to know one example, if we solve a system just with the naive Gaussian elimination, it will be pretty much clear to you how this method works. So for this, let's just see how this method works. We have this system of equation. There are three equations, and the unknowns are x1, x2 and x3. So we have to use Gaussian elimination method, naive Gaussian elimination method, to find out these values. Okay, so to find out these values, we need to first modify the original coefficient matrix into an upper triangular matrix. So how we do that? So we need to first eliminate this first column below this first equation. That means these 0.1 x1 and 0.3 x1, these two terms will have to vanish. Okay, then also minus 0.2 x2, this term will have to vanish. So if these three terms become 0, then the resultant matrix will be an upper triangular matrix. So that's our target. That's the first step of naive Gaussian elimination approach. So first of all, let's just vanish these two elements from the first column. So how we are going to eliminate this? Take the second equation. We need to vanish this 0.1 x1. So how we are going to vanish this? We are just going to use the elimination method that is a non-computer method that we have learned, that we have seen in the previous lesson. So we multiply this first equation by 0.1 by 3. So we multiply this first equation with this value 0.1 divided by 3. So once we multiply the first equation by this term, in the first term of the first equation, these 3 and these 3 will be cancelled out, and we will have only the 0.1 term. That means 0.1 x1 and blah blah blah. So the first term will become 0.1 x1, and look at this, in the second equation also we have the term 0.1 x1. So we subtract the first equation from the second equation and replace the resultant value in the second equation. Okay, so once we subtract this value, So once we subtract the first equation from the second equation after multiplying this value, we will get this equation, that means 0.7.00333x2 minus this and equal to this value. So this is the modified second equation. So we are going to replace this second equation by this version. So look at this, in this modified version we do not have the first term, that means this x1 term, this will be vanished after the subtraction. So let's get to the third equation. So how do we eliminate this 0.3x1 term? So we have to multiply this first equation by 0.3 divided by 3. Okay, in the first case, whenever we are eliminating the second equation, we are just multiplying the first equation by this value. Look at this 3. In both these cases, we are just in the denominator we have the 3 term, because 3 is the pivot element. Okay, so we are just multiplying the first equation by this value 0.3 divided by 3, and in that case these 3 and these 3 will be cancelled out, and we will have only the 0.3x1 and blah 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 the next terms. So in the first term we will have only 0.3x1. And look at this, in the third equation we have 0.3x1. So if we subtract the first equation from the second equation, we will get a modified third equation, which is something like this. Okay, so now we have the third equation, and we will replace this original third equation by this value. Okay, so once we subtract this value, we'll substitute this new equations, we will have this modified version. But this is not the upper triangular matrix. Our calculation is not over yet. Okay, we will have to also to eliminate this term. This is because this term is also below the principal diagonal. Okay, so we will have to vanish this term. So now we have completed our first step. We have just eliminated the first terms from the first column of the original coefficient matrix, and now we have to eliminate this term from the second column. So how we are going to use this, subtract this? Remember, where after the first term the pivot equation becomes this one. So in the first step our pivot equation was the first equation and pivot element was 3. In the second step our pivot equation will be the second equation, the modified second equation, and the pivot element will be 7.00333. So this is the pivot element now. So based on this second equation we will have to eliminate this term. So how we are going to eliminate this? We are just going to multiply this second equation, the modified version, by this value. Look at this, in the denominator we have the pivot element, that is this term. So once we multiply the second equation by this value, this 7.0033 term and this 7.0033 term will be cancelled out, and we will have only this term, that means minus 0.19 into x2. And also in the third equation we have the value minus 0.19 into x2. So once we get this value, we just subtract this modified version from the third equation. Okay, after the subtraction the result will be something like this. So this is the modified third equation, and we are going to substitute these third equation with this one. And once we substitute this, we will get the final upper triangular matrix. Look at this, on the left hand side this is an upper triangular matrix. Okay, on the left hand side this is an upper triangular matrix. So our first step of the naive Gaussian elimination is done. We have successfully converted our original coefficient matrix into an upper triangular matrix, and the second step begins now. The second step is the back substitutions. That means we are going to start from the last equation. Look at this, in the last equation of the upper triangular matrix, this is very straightforward. We can easily get the value of x3 by dividing this value with this coefficient. That means x3 equal to 70.0843 divided by this coefficient, which is 7. So from the third equation we have easily got the value of x3, and we are going to use these value of x3 into the previous equation. That means in the second equation. So from the third equation we have determined x3. We are going to substitute these x3 into the second equation, and then after algebraic manipulation we will get the value of x2. So this is the calculation. We have just substitute the value of x3 into the second equation, and then we multiply this and get the result of x2, and which is something like minus 2.5. So once we get the value of x3 and x2, we are going to use these two values into the first equation to get the value of x1. So in the first equation we have three unknowns, x1, x2 and x3, and we have already determined x2 and x3 from the last two equations, and we are going to use those values in the first equation to determine the value of x1, which is 3. So in this way we can get all the unknown variables through back substitution, and we have got all the results of x1, x2 and x3. I hope you all understand how the naive Gaussian elimination method works out. But there are some pitfalls of this naive approach. If you remember, in each of the cases, whenever we eliminated the first column, second column in the first step, that means the elimination step, we have said that the first coefficient was denoted as the pivot coefficient, and in each of the calculations we were just dividing with the pivot coefficient term. But if this pivot coefficient term is 0, then the naive Gaussian elimination approach will not work, because in that case we are going to have an infinite value, an unknown value. We cannot use the naive Gaussian elimination, because if the pivot coefficient vanishes, if this is 0, then there is no way the naive Gaussian elimination is going to work out, and that is the first pitfall of the naive approach. Also, there is an issue of round of error. When large number of equations are considered, in each of the cases, in each of the steps, a substantial amount of round of error is included, and as a result, whenever we have say 1000 equations in the system, in each step we are going to incorporate some round of error in each of the terms, and as a result, after the whole calculation, the error term might accumulate, and as a result it will get higher and higher. So we need to be assured that we are using a substantial amount of significant digits whenever we are calculating with the naive Gaussian elimination approach. Also, there is a third pitfall, which is due to the ill-conditioned system. For example, look at this. This is a system of two equations. The first coefficient is 1, and the first coefficient of the second equation is 1.1, and if we use the naive Gaussian elimination approach and solve for the unknown variables, we will get these results: x1 equal to 4 and x2 equal to 3. But if we just manipulate the second coefficient of the first coefficient of the second equation a little bit slight. For example, we have just changed the value from 1.1 to 1.05. So this is a very small change, but due to this small change, look at the effect. The solution is completely different. x1 equal to 8 and x2 equal to 1. So for just a simple and a very small amount of change in the coefficients, the result is drastically changed. Okay, so think about this. So whenever we have hundreds of equations and we just calculate with a certain number of significant digits, in all of the steps we will change the original coefficients. That means a certain amount of round of error will be incorporated in each of the steps. That means the result might change, the original results might change. So this is the case for ill-conditioned system. Okay, so this is another pitfall. Also, we have a fourth one, which is a very significant one. Let's say whenever we have a system of equations, two of the equations are similar. Okay, so what will happen? That means, let's say we have three equations and three unknowns. That means x1, x2 and x3. But it turns out that two of the equations are similar. So what will happen? Now we have actually two equations with three unknowns actually, so we cannot solve such a system. We need to need a system where the number of unknowns are equal to the number of equations. So once there are two identical equations in the system, we cannot use the naive Gaussian approach. So there's another pitfall. Such systems are called singular systems. So in this lesson we have learned about the naive Gaussian elimination approach. So I guess you understand the examples and the algorithm that we have used. So please go through the example that we have used in this slide thoroughly and try to understand the details of that example. And also please try out the MATLAB code that I have attached with this slide. So please go through that MATLAB code and you will understand so how to use the Gaussian elimination approach for hundreds of thousands of equations, which is not possible for hand calculation. So in the next lesson we will use another extension of this naive Gaussian elimination approach, because we have seen there are some pitfalls of this naive approach. So we have to make this method a smarter one. That means we are going to find out some techniques that is thoroughly used to make this Gaussian elimination method an effective one. So we are going to find out the details of the smart Gaussian elimination approach in the next lesson. So till then, thank you so much.